All right, let's see where we left off. All right, so what did we learn last time? We learned that bromination of an alkene cannot go through a carbocation intermediate. We learned that because of this experiment right here. When you run this experiment and you do this reaction with bromine, if it was a carbocation intermediate, you would get anti and syn addition, and we don't get syn addition, so it means that our proposed mechanism that we came up with on the previous page is incorrect. Because if it was correct, we make a carbocation, we're going to get syn plus anti. So it turns out we only get anti, and you need to remember that. So we've got two new stereocenters. We're going to get enantiomers, bromines on opposite sides, so anti-addition. So let me show you a mechanism that is consistent with this stereochemical outcome. And I think, I don't know why it did that. Weird stuff moving around. So you've got that right on your page, so we're just going to keep going. So what we talked about was in the vicinity of the pi bond, that's looking a little crazy. That bromine-bromine bond gets polarized. And so, so what's going to happen is, and I will probably have to redraw this down here because you're not going to be able to see what happens. I'll redraw it down here, and you can, it'll look good on your page. All right, so let's redraw this. Why is it doing that? Okay, let's try that again. Don't save. Cancel. Oh, come on. Now, right now, when we're already caught up, we can't have this happen again, right? Awesome. Look at that. Okay. So I have to redraw this. You don't. I think it's because I took a space out, because things weren't scrolling right, and I didn't realize it would do that. All right, so we get polarization of the bromine-bromine bond. Oh boy, I didn't leave enough room for this, but let's work on this here. Okay, so I'm going to have the lone pairs on this bromine. I'm going to have the lone pairs on this bromine. So go ahead and add, I already have that on there. And let me in a different color so we can see what's going on a little more clearly here. This pi bond's going to attack this bromine. We're going to break the bromine-bromine bond here. And then one of the lone pairs on this bromine that's closest to the alkene is going to come down and attack on the other side. That's what the arrow pushing should look like. So basically what we're doing is we're adding an extra arrow to the previous mechanism that we were proposing. And what that does when you do that, now I get to go back over here. It makes a new functional group that we have not talked about. It's called a bromonium ion. I'm going to keep stereochemistry here of the alkene. I remember I tilted the alkene to make this a little easier to see. All right, so this is what we call a cyclic bromonium ion. Or you can just call it a bromonium ion. So this is a cyclic bromonium ion. And so then what's going to happen next is the bromide ion that we just had leave here in the first step, Br minus, is going to do backside attack. And just like when and what this is going to remind you of is an epoxide. Bromide's going to do backside attack, and so you're going to get inversion of configuration. At the carbon being attacked. I'm going to have bromide ion come in and attack from the opposite side. On the left-hand side. So boom, this is going to come here. I'm going to have an attack on the left-hand side. Both sides are equally substituted, so it doesn't matter which side we attack on. Both sides have one methyl group. And if you're able to draw stereochemistry from epoxides, this will be very easy for you. So the bromide comes in from the opposite side. So we're going to have Br here. We're going to have Br here. On the left-hand side, the hydrogen moves up, but it's still going back. On the left-hand side, the methyl also moves up. We'll just do Me here. And on the right-hand side, it stays exactly the same. So overall, that's inversion of configuration. Some students are still having trouble with why that's inversion. All we did, of course, was to move this methyl up and this hydrogen up. But you can see that it's inversion because in this product right here, the bromine's on this side, and over here it's on the opposite side. So that is inversion, just like inverting the umbrella, just like we did with SN2 reaction back in chapter 7. And so that mechanism accounts for the fact that we get anti-addition only. We will also get the enantiomer. There's two ways you can form the enantiomer here. I'm going to show you both ways. That'll be on the next page. The enantiomer is formed when bromine comes in from the bottom. Let's see what that looks like. So we have this, I'm still tilting the alkene to make the stereochemistry a little bit easier to draw. And so we can have the bromine coming in from the bottom instead. We had the bromine coming in from the top, because remember, this alkene is planar, and so the bromine can come in from the top. That's what we showed on the previous page. It can also come in from the bottom, so that's what we're showing here. So this will give us another opportunity to practice the mechanism for this reaction. So we're going to attack this bromine. We're going to break the bromine-bromine bond. And then one of the lone pairs from bromine, I usually just do whatever's closest, goes right here and attacks the carbon on the other side. So very, very, very reminiscent of epoxides. So there's your cyclic bromonium ion, which has a positive charge on bromine, and that's going to behave exactly the same as a protonated epoxide. And then I'm going to have bromide ion come and attack on the left-hand side again. So that's one way to get the enantiomer. There's also another way. Bromide ion is going to come in and attack from the opposite side. So I always draw the incoming groups in the plane, and then that makes it easier to draw the stereochemistry here. There's the hydrogen. Here's the methyl. Hydrogen here. There's the methyl. So that's the enantiomer. That's one way to get the enantiomer. The other way to get the enantiomer is to have bromine attack on, draw the same bromonium ion we did on the previous page, but have bromine come in from the right-hand side. Since this is equally substituted on both sides, there's a 50% chance the bromine's going to attack on the left-hand side, and there's a 50% chance it will attack on the right-hand side. So it can attack on the left, it can attack on the right, from this one here. So I had this coming in on this side. We can also have that coming in from the opposite side. So I'm going to redraw the bromonium ion from the previous page. So we already showed how to form that. So from the previous page, and then I can have bromide ion coming in from the right-hand side. We break the carbon-bromine bond, kick electrons up onto bromine. And so it will look like this. Hydrogen going back, just moved up a little bit. Methyl coming forward, just moved up a little bit. Over on the left-hand side, we have the bromine on the top, and we have hydrogen going back and methyl going back. These two are the same. They don't look like it, but they're the same. They have the same stereochemistry. It's the enantiomer of the one on the left. I guess they do look the same, don't they? Now that I look at it again. Only difference is I wrote Me instead of methyl, but they're exactly the same molecule. So that's the way that we would show the enantiomer. Okay, questions? Anybody? All right, important points about halogenation. Unlike a normal carbocation, all of the octets are satisfied in the bromonium ion. The bromonium ion has considerable ring strain, however, and there's a positive charge on the bromine atom, so this is a reactive intermediate. It's unstable, just like a carbocation is unstable. This is also unstable. Because a carbocation does not form in this reaction, no rearrangements are seen. We're not forming a carbocation. We saw we can't, because the stereochemistry tells us we can't form a carbocation. The product results from stereoselective anti-addition to the double bond. The reaction does not work with F2. It reacts explosively, nor with I2. It's thermodynamically unfavorable. So we're really going to see this mostly with bromine or chlorine. All right, so Br2 or Cl2 only. If the reaction is run in water rather than methylene chloride, a different product is obtained as the major product. Let's draw that. So we've got two possibilities. Let's see where we get those two possibilities from. All right, notice this is no longer symmetrical, is it? The previous example, we had a methyl on both sides. This is no longer symmetrical. We have one R group on the right, and we have two R groups on the left. So let's look at what our possibility is. What we form when we use bromine in water rather than an inert solvent is we get a bromohydrin. So bromine on one carbon, hydroxyl on the other. There's two possibilities here. Hydroxyl on the left, hydroxyl on the right. So two possibilities, hydroxyl on the left, on the right. And for each of those, we would get an enantiomer. So there's four possible products here. So that'd be this plus enantiomer, this plus enantiomer. And what do we actually get in this reaction? We get only this product right here, plus its enantiomer. We don't get any of this. And this is called a bromohydrin. Bromo for the bromine and hyd for like hydration for the hydroxyl. All right, so this is going to be a little, we have to explain that result, don't we? We're also going to form a bromonium ion in this reaction, just exactly like just when you do it with regular bromine. We're going to form a bromonium ion. In the second step, rather than bromide attacking, water attacks instead. But it's otherwise it looks the same. So if you think about it, we make the bromonium. There are two nucleophiles present. Two nucleophiles present then can attack that bromonium ion. There's water and there's bromide ion. If bromide ion opens up the epoxide, you get a dibromo compound. If water not the epoxide, if bromide ion opens up the bromonium ion, you get a dibromo compound. If water opens up the bromonium ion, you get a bromohydrin. Since we're using water as a solvent here, the concentration of water is much, much larger than the concentration of bromide. Since H2O is a solvent, concentration of H2O is going to be much, much greater than the concentration of bromide ion. So the nucleophile that's going to be mostly attacking is, and I shouldn't draw it that way. Let me fix that. We want concentration here. So that means that collision with water is more likely. So therefore, bromohydrin is the major product. Even though we have the possibility of forming a vicinal dibromide, we don't tend to get that because we've got so much more water than bromide here. So bromohydrin is the major product. So let's draw the mechanism for this. And it's going to look really similar. Once again, to help us with stereochemistry, I'm going to tilt the alkene so it's perpendicular to your page. And we still have bromine coming in, and we're going to still get polarization of the bromine in the vicinity of the pi bond. So the pi bond is going to attack bromine. We're going to break the bromine-bromine bond. And then one of the lone pairs remaining on the closest bromine is going to attack whatever side is convenient. This arrow is coming from the left, so I have the arrow coming in on the right-hand side. So ethyl on the left going back, methyl coming forward. On the right-hand side, hydrogen going back, methyl coming forward. This bromine has two lone pairs, two sets of lone pairs, and a positive charge. And we saw we got the product where the hydroxyl only came in on the most substituted side, so that's the way I'm going to show this. The water is coming in on the most substituted side. Is that reminding you of something? Yeah, it's just like in a protonated epoxide. And this is going to behave exactly like a protonated epoxide. So if you know your epoxides, this is going to be an easy mechanism for you. So we have water here coming in. Bromine is anti to the water that just came in. Stereochemistry on all of the groups attached to the alkene are going to stay exactly the same. So ethyl's still going back, methyl's still coming forward. And then in the last step, water's going to deprotonate the bromohydrin. So if I put this mechanism on the test, which I have many, many times in the past, it's a possible mechanism on the non-midterm too. If I put it on the test, I would only have you show the mechanism for forming one enantiomer. You don't need to form the other one. If you know how to do it once, you know how to do it again, and there's no reason for you to do it twice. Okay, so but the question is, how do we get the enantiomer here? Because you're going to form the enantiomer, you have to, because you started with achiral reagents. Everything's achiral. You have to get a pair of enantiomers. How do we get the enantiomer here? So we certainly can't have water attacking on the other side to get the enantiomer, because we don't get any water on that side. Yeah. Yeah, bromine can come in from the bottom. That's how we form the enantiomer. All right, so we're going to write plus E Br2 comes in from the bottom. All right, so this is very similar to a protonated epoxide. And so we want to explain why we get this regiochemistry. And our explanation is going to look just like the explanation we used for an epoxide. All right, so let me just to jog your memory. So if you crammed the day before the midterm, you've forgotten this already. Okay, because you only get, if you cram, you only retain like what, 5% or something. Okay, so recall, let's compare this. I want everybody to see the connection here. So when we have a protonated epoxide, and I said this is going to behave just like a protonated epoxide, water came in from the most substituted side. Hopefully you did that on your test. So this is looking just like that. And what we have in common is we have a 3-membered ring here that has a positive charge on it. So this is all old news here. So then we had water, and then in the last step, we deprotonated. So hopefully you will see the similarity here. We get the 1,2 diol. Okay, so we went through an elaborate explanation for why that happens with epoxides. What we did is we drew resonance structures for the protonated epoxide, and we saw that there was more partial positive charge on the carbon that was more substituted. We're going to use the same exact explanation here. All right. So two possibilities. We're doing something a little bit unusual here. We're breaking sigma bonds, which we don't usually do when we're drawing resonance structures, but it is legal. As long as all atoms stay exactly where they are and we're just moving electrons, it's legal. So that would give us this structure right here. Alternatively, we can break the bond on the other side. If we do that, we get the carbocation on the right-hand side. And so then what we did was we drew the hybrid of the two best. So we took this one and we took this one. And that one's best because this is a tertiary carbocation, and here this is a secondary carbocation. So then we drew the hybrid. So then we have our hybrid here. And we just did the hybrid of the two best. And so we have a dotted line right here. That's a partial bond. We have partial positive on the bromine, partial positive, and we have partial positive here. And so the nucleophile, in this case our nucleophile is water. Water's going to attack on the most electron deficient carbon. So that's what we're going to do here. Just like this, it's going to attack on the most electron deficient carbon. And again, this is the hybrid of the two best resonance structures. All right, and it turns out that when you have unsymmetrical alkene and you're just using bromine without water, same thing is happening. The nucleophile is attacking on the most substituted side. It's just that we can't detect it. We just can't detect it because since both bromines are the same, there's no way to detect that in this reaction. But when it's a hydroxyl, we certainly can. So all I'm saying is that when we have an unsymmetrical alkene, which we do here, we're still going to form a bromonium ion. So I'm going to have the isopropyl here going back. I'm going to have hydrogen coming forward. We are still attacking on the most substituted side. It's just that there's no way to detect that, since both atoms are going to be the same. Questions on bromination? Anybody? Yes? Oh yeah, that's right. So yeah, thank you for pointing that out. I forgot that. What is it on your version? Is it a hydrogen? Yeah. This should be an ethyl. Change that to an ethyl. Ethyl, ethyl, ethyl. Thank you so much for noticing that because I completely forgot about it. So on your version, ethyl, ethyl, ethyl. Otherwise, when you go back and look at that, that's not going to make any sense at all. Okay. Just glad we got some eagle eyes here catching that. All right. There's one more reaction that we're going to talk about, and then we're going to do some synthesis. So we're moving very quickly into synthesis. I opened up Sapling Chapter 10. The last 10 problems are difficult synthesis problems. So I want you to wait until you're ready to go with those 10 problems. And you want to really honestly try them. If you get stuck, try to get help rather than, I don't know, what do? You guys go online and you find the answers on Facebook page, all that kind of stuff. My son filled me in on all of this. So that's not going to help you because it's something that you need to be able to understand on your own. And if you don't understand it, you're not going to understand it on the midterm when it's slightly different. So we'll get to that at the end of class. We might not get to it today, but I want to talk about hydroboration. So it'll probably be Friday. So you may want to wait until Friday to do those last 10 problems. Okay, addition of borane. So borane is another electrophile that adds to alkenes. When the addition is complete, you add peroxide and base, and the boron is turned into a hydroxyl. So this is another way to make alcohols. The difference with this method is that when we hydrate an alkene, we have a Markonikov addition. When we use hydroboration, it's what we call anti-Markonikov. It's the opposite regioisomer. And so both of those reactions are going to be really important to us in synthesis, because sometimes we want the hydroxyl on the least substituted side, sometimes we want it on the most. So we've got to need these, we need these two reactions to be able to do that. All right, so let's just give you a little background here. So BH3 and THF. And it turns out we don't really worry too much about the stoichiometry here, but this is a 3-to-1 ratio. So you have 3 alkenes for every 1 BH3. And so the BH is going to add to the alkene, and then and so then what it looks like, it's going to look, so here's what it looks like. I'm going to circle the atoms that we just added. Oh, no, actually, let me do this. I'm going to mark right here the original alkene. Those are the 3 carbons. I'm going to mark that right here so you can see that. That's the original alkene. And then the groups that we added on, let's circle those. I'm going to circle the first one here. What type of addition is that? The boron and the hydrogen are added to the alkene. It's a syn addition. And this happens 3 times. So here's the boron and that. Let's do a different color here for this one. This is the boron here, and that's the hydrogen here. Syn addition. And I'm having too much fun mixing colors here. There's the boron here, and there's the hydrogen. Syn addition 3 times. So we don't always draw it all out. It's a little bit it looks kind of spidery, and it's not a little difficult to see. This is often written in a shorthand way. Often written as this, Br2. Here's the hydrogen that just came on. Here's the boron. And rather than drawing all 3 groups, we just draw it once, and the R2 means that there's 2 other groups like that. It's just a shorthand way of writing it. So this R means that 2 groups identical to the one shown. So this is the first step. Right here is the hydroboration. The second step, and really important that when you do this as a synthesis and you're filling in reagents, that you separate these into 2 steps. First you do the hydroboration, and then the second step you do basic hydrogen peroxide. And what you get is 3 of the alcohols. Again, I'm drawing in that hydrogen on the carbon where it just came in. So what we've done is we've done a syn addition of water to the alkene. Do you see that the hydroxyl is on the least substituted side rather than the most substituted side? Hydroxyl's on the least substituted side, so this is an anti-Markonikov addition. It has the opposite regiochemistry of hydration. If you did a hydration, then the hydroxyl would be on this side, right here, the most substituted side. So this is on the least substituted side, so this is an anti-Markonikov addition. And it's not going to let me go off the edge of the paper, so just go ahead and add your little N there that I left off. Anti-Markonikov addition. All right, let's look at a typical reaction. BH3, THF. How do you make BH3? You take B2H6, which is a gas, and you add it to THF. We'll talk about that in just a minute. What that does, step 1. Step 2, basic hydrogen peroxide. So what I'm going to be looking for, you can leave the water off, but I want to see H2O2 and I want to see hydroxide for step 2. And as you can see, overall, we have addition of water across the double bond after those 2 steps. So this is a hydration across the double bond. And we can see if we circle the groups that just came on, we've got this hydrogen and this hydroxyl, syn addition. Hydroxyl on the least substituted side. So this is not Markonikov, it's anti-Markonikov. Will we get the enantiomer here? How do we know? Will we get the enantiomer here? So what we said is if you start with things that are achiral, and all reagents are achiral and there's no chiral influence, if you form new stereocenters in your product, you will get a racemic mixture. You absolutely have to. So our alkene is achiral. This is achiral, peroxide, sodium hydroxide is achiral, so you will get the enantiomer. And we have graduated now. We're allowed to write just plus E on the test rather than drawing out the enantiomer. This is because you guys are so mature now. I know that you're ready for that. Big step. Be careful how you wield that plus E though, because some reactions don't have an enantiomer. So if you write the correct product and you write plus E, you don't get any points because there isn't an enantiomer. And if somebody draws the wrong enantiomer, they get it wrong. So why should you get it right when you write plus E? Okay, so be careful where you put plus E. Some people put it on every single problem, and that can cost you. So make sure you know what you're doing. So highly regioselective and stereoselective reaction, anti-Markonikov addition of water to an alkene, and so it's opposite the regiochemistry. Of a H2O, H3O plus addition. And so no rearrangements are observed. Now, this is one, I'm going to show you the very first part of the mechanism. I will not show you the oxidation. If you are curious as heck about the oxidation, you can come to my office and I'll show you. But, so I'm not going to ask you this mechanism on the test, but you do need to know this reaction. You will use this reaction over and over again in synthesis problems. So I'm just going to show you the first part of it because for some of you it will help you remember why it's a syn addition. Okay, so that's why I'm showing you. All right, so BH3 is a Lewis acid and therefore an electrophile. So if you take B2H6 plus, this is THF, by the way, tetrahydrofuran. And you can certainly use the abbreviation for THF. You can use THF in your mechanisms. And what this is going to do is break apart the B2H6 into BH3. So we'll have a positive charge on oxygen, we'll have a negative charge on boron, and that's equivalent to BH3 dot THF. So that's the shorthand way of writing that. So what's happening here is boron is accepting an electron pair from the oxygen atom of THF. So boron accepts an electron pair. Classic Lewis acid-base reaction from the oxygen atom of THF. Then what happens? Let's show it right here. Pi bond grabs this hydrogen. Let me do that again. I didn't leave myself enough room. All right, in this particular reaction, we don't have the pi bond attacking. We're actually transferring hydrogen with its pair of electrons. So is H minus, is that a nucleophile or an electrophile? It's an electrophile, it's electron rich. So what's going to happen is, if you look at the polarization of this bond, pi bond does not grab the hydrogen. The pi bond comes and attacks the boron. And the hydrogen-boron bond is going to break. The arrow is coming from the hydrogen-boron bond. And the hydrogen is being transferred with its pair of electrons, so it's like a hydride. So hydrogen transfers. This is not a proton transfer. This is a hydride transfer. Transfers with its pair of electrons. So as H minus, whoops. As H minus, not H plus. All right, this is what the transition state looks like. Again, you're not going to have to show this on the test, but I want you to see that how we get our stereochemistry here. That's what the transition state would look like. If you do this, I'm missing my second arrow here, or my first arrow I'm missing, just like that. We have a partial negative charge on boron, and we have a partial positive charge on carbon. How would you get those charges? If we did it stepwise, and we had this bond form first, that would leave a positive charge here. And then the hydrogen is attacking the positive charge. Okay, so that's one way to think of it. Again, you don't need to draw this. But as you can see, the boron and the hydrogen have to come in on the same side. There's not room for this hydrogen to come up here and the boron to be up here. That would be geometrically impossible. So the boron and hydrogen come in on the same side. And that's how we get our stereochemistry. We call this a four-center transition state. So that's what the transition state looks like. And then, so we have there, here's our syn addition. And we can see that if we look at the groups that just came on, they came in on the same side. And then we do this 2 times more. And that's what we get. So that's the hydroboration step. 3 things to notice. The positive charge is on the carbon that will lead to the most stable carbocation. If we were going to form a carbocation, the bulkier BH3 group is on the least substituted side. So that's a good way to remember stereochemistry here. Bulky boron on least substituted side. So a little bit of alliteration there to help you remember. Bulky boron on least substituted side. And boron and hydrogen are added to the same side of the molecule, so it's a syn addition. Because of the fact that the bulkier boron is on the least substituted side means that steric factors are important. Sorry, you guys are changing page and page. I gotta watch that. Because we have the partial positive charge on the carbon that leads to the most stable carbocation, we know that electronic factors are also important. So there's many things going on here. In this step 2 of the oxidation of the organoborane, I'm not going to show you the mechanism. Again, you can come to my office if you want to see that. But let's look at the overall stereochemical outcome, because that is very important for us. Here's the methyl. Here's the hydrogen. When we oxidize, we replace the boron with oxygen exactly where the boron is. There's no inversion, it's retention of configuration. So this boron's going to become an OH here. So important points about this is that the OH replaces boron with retention of configuration. And please skip this mechanism. I will not ask you hydroboration. I won't ask you the first part. I will not ask you the second part. I will not ask you hydroboration mechanism. You will have to learn this very important reaction for synthesis. You will use it many, many times. But skip mechanism for oxidation. I'm not going to show it to you. All right. That's a great stopping point. We will continue this on Friday.